Alright, today I want to look at sigma notation, and sigma is a letter of the Greek alphabet, as you see here, and it represents, in math, finding the sum. So we want to learn how to work with this. Here's a typical expression. We want to find the sum of the terms of the form 3k plus 1 as k varies from 1 to 4. So the way this works is you take the bottom number, you plug it into the formula here. So if k is 1, we have 3 times 1 is 3 plus 1 is 4. So 4 would be the first term. Then we pick the next number after 1, so 2. We plug in 2 here. 3 times 2 is 6 plus 1 is 7. Okay, now we're going to put in k equals 3. So 3 times 3 is 9 plus 1 is 10 is the third term. And the final number I'm going to put in is the number up here. So I've put in k equals 1, k equals 2, k equals 3. In order to get these numbers, the final number is k equals 4. 3 times 4 is 12 plus 1 is 13. And this is my series in what we call open form. All of the terms shown added together. And that equals the answer in nice closed simplified form, which in this case would be 34. Alright, we have c being a constant, c being a real number, and we've got this expression. So if we plug in k equals 1, k equals 2, k equals 3, we get the term ca1 plus ca2 plus on and on and on until I plug in n as the last term, can. Alright, what I can do with this expression is I could factor out a c. And so because I can do that, I could write this expression as the sum of the terms a sub k multiplied by c. So I'm just trying to point out that if you have a constant times an expression that changes with k, the constant can be pulled out front, and then you can just sum up the terms of the form a sub k. Alright, here's another expression, the sigma of a sub k plus b sub k. Again, let's find each of the terms. So if we plug in k equals 1, we get the first term. K equals 2, we get the second term. K equals 3, and so on. And we keep doing this endlessly, on and on and on, dot, 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 until we get to our final plug-in of n, so plus a sub n, b sub n. Alright, now what I'm going to do is I can reorganize all of these terms like so. And so I could write that expression as the sum of the terms of a sub k plus the sum of the terms of b sub k. Okay, here's another property of sigma notation that we will put to some use in a moment. If I wanted to find the sum of the terms of the form k as k varies from 1 to n, first term would be 1, k is 2, second term would be 2, and so on. The last term would be n. So if I wanted to know what 1 plus 2 plus 3 plus 4 plus dot 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 up to n added up to, I'm being told that this open form, the sum of the terms, is equal to this closed form, this formula. Okay, if I just think about this for a second, so I'm saying that if k went from 1 to 3, that would be 1 plus 2 plus 3. I can see that that adds up to 6. I should get the same result if I simply plug in my n value into this formula, which is 3 times 3 plus 1, 4 over 2. Sure enough, I get 6. Okay, at this moment you just need to know the existence of these properties, and we'll be putting them to use in a moment. By the way, if you wanted a bit more explanation in terms of why this is equal to this formula, here's an argument. I have the terms 1 plus 2 plus 3 up to n. So that's the sum of those n terms. I'm going to rewrite this sequence in reverse order. So n plus n minus 1 plus, this would have been n minus 2 plus, this would have been 2, and this would have been 1. Okay. Now if I add these two terms together, it's like a system of equations. Sn plus Sn is 2Sn. Now you'll notice that if I add these, I get n plus 1 every single time. Here's n plus 1. If I add these, n plus 1. If I add these, n plus 1. So I'm getting a sum of n plus 1, how many times? N times. And then if I divide by 2, I can see that the sum indeed is n times n plus 1 divided by 2, which is what my formula was. Okay, next property that we will put to some use in a moment is that the sum of the numbers of the form k squared, so 1 squared plus 2 squared plus 3 squared up to n squared, can be calculated by this formula. And for numbers of the form k cubed, the formula is as follows. All you'll need to be able to do at this point is to use these formulas to simplify more complex expressions. Okay, let's put these formulas to work. I want to simplify this expression, which, if I think about it, just means the numbers as follows. Plugging in 1, I would get 3. Plugging in 2, I would get so. And plugging in 100, I would get 3 times 100 squared. So I want to know what all of this adds up to, okay, without actually having to write out all the terms and figure that out. So applying my properties, one thing I could do is I could pull the constant out front. So I could write 3, the sum as k goes from 1 to 100 of k squared. So I know already that numbers of the form k squared as k goes from 1 to n is given by this formula, which we just mentioned earlier. All I need to do is, because this is of the same form, just replace the n with 100. So 3 times 100, 100 plus 1, 101, times 200 plus 1, 201, divided by 6. If I evaluate that expression, that is what all of these terms would add up to. Okay, let's look at this example. We want to simplify this expression, the sum of the form k squared over n. So the terms here would be 1 squared over n, plus 2 squared over n, plus 3 squared over n, plus all the way up to n minus 1 squared over n. Okay. Well, we can see that all of these terms have a denominator of n. So we can pull that constant out front. 1 over n, the sum as k goes from 1 to n minus 1 of k squared. What I'm trying to do is set up my expression here to be similar to one of the sigma formulas for k squared. Now the problem is that my formula up here has an n in it. So what I could do is I could break this blue part up as follows. This would represent the sum of all the terms up to n, but I only want the sum of all the terms up to n minus 1 squared. So what I'd need to do is take off n squared, because if k was n, plugging it in there, I would get n squared. I don't want this, so I got to take it off. Alright, so I'm going to simplify this expression. From my formula, I'm going to get this to be n times n plus 1 times 2n plus 1 over 6 minus n squared. And let's just simplify this expression. We could distribute this through. That would mean that the n's would cancel out of here and here. So we'd have on the top just this. And we could simplify that, 2n squared plus 3n plus 1 over 6 minus 6n over 6, which reduces to 2n squared minus 3n plus 1 all over 6. And there is my simplified form in closed form.